Now it's time to revisit some of the periodic trends and look at them in terms of ions that are formed. So remember when we talk about the size of an atom or the atomic radius, across a period, the radius generally decreases. You can check this out by looking at your fancy periodic table. The reason for this is because you're adding a proton and an electron to the same energy level. So there's greater attraction between the positive nucleus and the negative electrons, so the radius decreases. Down a family, the atomic radius always increases. This is because you're adding another energy level onto the atom, and that energy level is going to be further away from the nucleus. So the largest atoms on the periodic table can be found in the lower left-hand section. The smallest atoms on the periodic table are actually in the upper right-hand section of the periodic table. Now, how does this apply to ions? If we look at the metals in group number 1, family number 1, the size of the atom as you go down the table will increase because you're adding an energy level. Well, what about the ions? Well, for these metals, you are removing an electron, which means that you're going to have more positive charge in the nucleus than you have negative charge in the electron clouds. So there's going to be a greater attraction, and the size of the metal cations actually decreases compared to the neutral atom itself. Now the trend for the ionic radius is to still increase down the table, but metal cations are smaller than their neutral atom counterparts because there are more protons in the nucleus that can attract the electrons. The exact opposite occurs for nonmetals. The trend for atoms is still to increase in size as you go down the table, but nonmetal anions will actually be larger than their neutral counterparts because you're adding an electron, so you have more electrons in the electron cloud than you have protons in the nucleus. So there's not as much attraction to the nucleus and the electrons spread out a bit more. The trend is still for the size of the ions to increase down the table. Metallic cations are going to be smaller than their neutral counterparts. The reason being, you've lost a valence shell. You've gotten rid of the valence shell and now you just have the core electrons, so the smaller energy levels are closer to the nucleus. Nonmetal ions or anions are going to be larger than their neutral counterparts because you've completely filled that valence shell. You now have more electrons than you have protons, so the attraction to the nucleus isn't as great. When we think about the trend of ionization energy, remember, ionization energy is the energy required to remove an electron from an atom. And across a period, this trend is for the ionization energy to increase. It becomes harder and harder to remove an electron. Down a family, the trend is for ionization to decrease. It gets easier and easier to remove an electron as you go down a family. So the highest ionization energies are nonmetals because they don't want to lose any electrons. And ionization energy is, by definition, losing an electron. The lowest ionization energies are from the metals, especially group 1 or family 1 metals. They will easily lose that one valence electron to gain that noble gas configuration. That's why they have very low ionization energies. So in general, metals have low ionization energies, nonmetals have high ionization energies. So let's talk about ionic bonding. First of all, ionic bonding is the transfer of electrons from one atom to another. Generally speaking, this happens when a metal reacts with a nonmetal to form an ionic compound. Metals will lose electrons and give them to nonmetals. So there will be a transfer of electrons from a metal to a nonmetal. This makes the metal a cation because it loses an electron to become positively charged. The nonmetal gains electrons to become negatively charged, therefore it is an anion, and the ionic compound then is held together by the attraction between the positively charged cations and the negatively charged anions, and it makes a nice lattice-like structure. So to determine whether a bond is ionic or covalent, you have to look at a difference of a property called electronegativity. Electronegativity is an atom's ability to attract electrons when it's in a bond. If it does a very good job of attracting electrons, we're going to call it an ionic bond. If the atoms equally kind of attract the electrons, we're going to call that a covalent bond. So what we have to do is look at something called the percent ionic character, and to do that we have to use our fancy periodic table. So as an example, let's do the percent ionic character between sodium and chlorine. What we want to start by doing is looking up the electronegativity values in our fancy periodic table. Okay, if we look at the appropriate side of our periodic table, we can see that the electronegativity values are listed in the upper right-hand corner of each box. So the electronegativity for sodium is 0.93, and the electronegativity for chlorine is 3.16. What we want to do is find the difference between these two values, and then we're going to use the chart that's also on the fancy periodic table to determine the percent ionic character. So the difference between 3.16 and 0.93 is 2.23. So now we can use the table that's at the top of that same side of the fancy periodic table as the electronegativity values, and we can look to see that if you have an electronegativity difference of 2.23, that this bond is approximately 71% ionic character. That means it is 29% covalent character. Anything that has a percent ionic character greater than 50%, we're going to say is an ionic bond. And an ionic bond involves a transfer of an electron from one substance to another. A covalent bond involves the sharing of electrons, and that is something we're going to talk about at a different time.